Hello guys, good morning. Today in organic chemistry we are going to talk about alkanes, reactions of substitution. The first thing you need to know is that there are three general basic types of organic reactions. Number one, substitution. This is a reaction in which we change one atom for another and keep the same single bonds. To be able to conduct a substitution, we need a great amount of energy to be able to separate the bonds. This energy usually comes from ultraviolet light and/or heat. The second type of reaction is an elimination reaction. This is a reaction in which we remove atoms in pairs. It could be 2 atoms or 4 or maybe more at the same time, but if we use the same carbon-carbon bond, it's gotta be 2 atoms or 4 atoms. This is done with the help of an inorganic compound as a catalyzer. As a result, a double or triple bond could be formed. So we can get out 2 atoms, 4 atoms, or even more, but from different carbon-carbon bonds. The third type of reaction is called addition. In addition, we add atoms in pairs. 2 or 4 atoms could be added at the same time, which will form new single bonds with the electrons available from a pi bond. Remember, the pi bond is the weakest bond of a double or triple bond. So, alkanes, why substitution reactions? There are some important things you need to remember about alkanes. Alkanes are saturated compounds. That means that they are made of only single bonds. Another important thing to remember is that alkanes have very low reactivity. This means that they need a little help to react with other elements or compounds. When presented with another atom, element, or compound to react, alkanes do not care much. They are fine just the way they are. So if we want them to react, we need to give them a little help. Okay? Alkanes are not worried about reacting. The reason of this happening is that alkanes are very stable compounds due to their saturation, meaning, again, they have only single bonds. Another important thing to remember is that there are primary, secondary, and tertiary carbons. These carbons are related to hydrogens in any hydrocarbon. Therefore, the hydrogens become also primary, secondary, and tertiary. As you can see in this example, all the carbons that are at the end of the chain are primary carbons because they are only related to one other carbon. And they are also related to 3 hydrogens. If you take the middle chain, the third carbon is related to 2 carbons and to 2 hydrogens. Therefore, this is a secondary carbon, and those are secondary hydrogens. The next carbon to the right of that secondary carbon is related to 3 different carbons, as you can see, and only 1 hydrogen. This is called a tertiary carbon. Therefore, the hydrogen is also named tertiary. The carbon that we have here, as you can see, is related to other 1, 2, 3, 4 carbons. This is called quaternary carbon and do not have any hydrogen. Therefore, there are not quaternary hydrogens. They do not react. Remember, there are also quaternary carbons, but they are not related to hydrogens, only to other carbons. Okay? Which hydrogen is easier to remove or replace? That's a very good question. Remember, not all the hydrogens are the same, as we saw just yet. You have tertiary, secondary, and primary carbons, therefore the corresponding hydrogens. It's easier to remove a tertiary hydrogen then a secondary hydrogen, and finally a primary hydrogen. And why is that? You can say the primary hydrogen is here at the end of the chain, then the secondary is here in the middle, and the tertiary is harder to reach because it's here. So you might think it's the other way around. But the point of them being easier to remove has to do with a word that's called stability. Case of halogenation substitution reactions, what kind of help is needed? Halogenation is the replacement of one or more hydrogen atoms in an organic compound by a halogen. That could be fluorine, chlorine, bromine, or iodine. You have here an example of a 1, 2, 3, 4, and a methyl here, a 2-methylbutane that we are going to chlorinate. This symbol means ultraviolet light, and the main product is here. That means we are taking the hydrogen from the tertiary carbon. That is the least stable of all the carbons. Okay, to be able to remove an hydrogen atom from a carbon-hydrogen covalent bond, we need lots of energy, as I said before. We are going to take this kind of energy from ultraviolet light and or heat. How does ultraviolet light works? Ultraviolet light or UV light has the power to remove electrons from carbon-carbon bonds or carbon-hydrogen bonds because it has lots of energy. It's a light of high frequency. Therefore, this high frequency breaks the bonds and forms free radicals. You have here a spectrum of the light, and you can see the ultraviolet light in the left side, the infrared light in the right side, and ending with the microwaves, beginning with the X-rays. Here you have the X-rays, here you have the microwaves. So the ultraviolet light more to your left is a higher frequency ultraviolet light, therefore is stronger. And to the right, if you move to the right, you are going to get a different kind of ultraviolet light because the wavelength changes. Here you have more waves in the left, you have less waves to the right. Still is a very strong light. As you can see here, this is a compound that has electrons and you are injecting this compound with ultraviolet light, therefore you are making those electrons free. And these free electrons are also called free radicals. But wait, there is something else. Halogens have also a character of themselves, so they have lots to do with the replacement of a hydrogen and the yield of the reaction. The reactivity of halogens decreases in the following order. First you have fluorine, then you have chlorine, then you have bromine, and lastly you have iodine. But for better clarity, let's say that fluorine is like this, very explosive and reactive, and it's very difficult to control. On the other hand, you have iodine, which is generally unreactive. It's like asleep. So, for the replacement of a hydrogen with halogen, we are going to put our attention only on chlorine and bromine. And we are going to call that chlorination and bromination. What do you need to know? Number one, chlorination and bromination are normally exothermic, meaning that they release heat. Number two, energy input in the form of heat or light, like we already talked about ultraviolet light, is necessary to initiate these halogenations. This energy input is going to form the free radicals we need to begin the reaction. Number three, if light is used to initiate halogenation, thousands of molecules react for each photon of light absorbed. A photon of light is a quantum, a piece of energy. This means there is not only one single molecule that reacts. Number 5. We represent a reaction as a chemical equation. Remember, the equations are not representative of the thousands of molecules formed as free radicals, or the new compounds formed at the same time in a chemical reaction. So we have this equation only to have an idea of what's going on. Number 6. Halogenation reactions may be conducted in either the gaseous or liquid phases. And number 7. The most plausible mechanism for halogenation is a chain reaction involving neutral intermediates such as free radicals or atoms, as you are going to see in the next slide. These are the steps for the mechanisms of reaction of the chlorination and or the bromination. The first step is initiation. You have light. You divide the chlorine atom that it has two atoms into chlororadicals. Then you have this chlororadical, in this case reacting with methane, that is the most simple of all the alkanes. You release or remove a hydrogen from the methane and form hydrochloric acid, plus a new free radical that is methyl, because you remove a hydrogen from the methane. Then this methyl encounters another chlorine that is also separated by ultraviolet light, and then you have chloromethane plus chlorine alone as a free radical. The last step is the termination step.